Alright, welcome to Module 5. So we're going to explore Raspberry Pi, one of the most versatile single-board computers available. Now it plays a powerful role in building the Internet of Things and different applications associated with IoT. By the end of this lecture, you'll have a clear understanding of how Raspberry Pi could serve as an IoT gateway, a sensor controller, or an edge processor, and how to actually build and simulate real-world IoT systems using it. So, the Raspberry Pi has revolutionized the maker and developer communities. It's an affordable, compact, yet highly capable Linux-based computer that allows you to create fully functional computing systems with built-in support for GPIO, general purpose input-output pins, USB ports, Wi-Fi and Bluetooth connectivity, and full operating system capabilities. It's uniquely suited to connect with sensors, actuators, and cloud services in IoT environments. So let's begin by considering the role of Raspberry Pi in an IoT architecture. So typically IoT systems involve sensors that collect data, connectivity layers that transmit this data, and cloud or edge systems that process and act on it. The Raspberry Pi often sits between the sensors and the cloud. It reads sensor values, performs local data analysis or filtering, and then transmits only the essential data to a remote server. This reduces network usage and improves system responsiveness. Say, for instance, you're measuring environmental conditions like temperature, humidity, and air quality. The Raspberry Pi can collect data from each sensor at regular intervals, store it locally in a file or a database, analyze for anomalies, and then send alerts only when conditions exceed defined thresholds. This not only optimizes performance, but also allows for logic control or local logic control, such as turning on a fan if the temperature rises too high. So next, let's look at how to connect sensors to the Raspberry Pi. The GPIO pins, they provide the interface for this. So let's see if we've got an image of them. We've seen them before. Here's our graphic. Let's stick here. Okay. You can use the digital or analog sensors that we've talked about previously, depending on your needs. For digital sensors like motion detectors or digital temperature sensors, you simply use Python libraries such as RPI GPIO or GPIO 0 to read and write data to the pins. For analog sensors, which the Pi doesn't natively support, you'll need an analog to digital converter, an ADC, such as the MCP3008 chip, and that'll allow you to bridge that gap between analog to digital. Now once you're connected, the Python code will use input-output logic to continuously monitor the sensor values. For example, a single script can read the temperature from a DHT22 sensor and print it to the terminal or write to a log file. The Adafruit DHT Python library makes it easy to interface with this kind of sensor. So we've got libraries that help us to do certain kinds of jobs. Within those libraries are the functionalities that I talked about before, where I outsource the work. So let's talk about network connection. Well, it's the key element in IoT. Raspberry Pi can use various methods to send data to other systems. HTTP is commonly used if we're going to send to a web server or a cloud endpoint via REST APIs. Alternatively, we could use MQTT. That's a lightweight publish and subscribe messaging protocol. It's ideal for resource-constrained environments. It allows Raspberry Pi to publish sensor readings to a broker and subscribe to commands for a remote dashboard. For example, a smart home project could use MQTT to let a Pi-based controller publish temperature data while subscribing to commands like turn on heater. Popular brokers like Mosquito or cloud services like Adafruit.io and ThingSpeak are often used to manage these communications. One of the strengths of Raspberry Pi is its ability to perform edge computing. Now that means doing the computation close to where the data is generated, rather than sending all the raw data to the cloud. Now this is useful in cases where low latency is critical or connectivity is limited. The Raspberry Pi can run Python, Java, Node.js, these different codes to analyze and act on data immediately. It can even support machine learning interface with lightweight models such as TensorFlow Lite. That allows for applications like image recognition or predictive maintenance. Now you're going to have a mini project, and you're going to be applying these concepts in Module 5 and Module 6. You've got projects. And in Module 5, simulate an IoT solution using Wokwi. Now, you say, well, what's Wokwi? I mentioned it before. Wokwi, here's the webpage, wokwi.com. You'll see a link in the resources page. This allows us to simulate the different SBCs. And we can go use these SBCs, interact with them, write code, interact with VS Code to the SBC without having to have an actual SBC. Whether it's Arduino, Raspberry Pi, whatever we're going to do. Okay, so there's the platform that we'll go play in, if you will. From there, your goal would be to build a basic environmental monitoring system with virtual sensors, program it using Python, simulate MQTT-based communication, or data logging functionality. The project highlights multiple layers of your learning. You'll get hands-on experience in sensor interfacing, GPIO control, Python scripting, network protocols like HTTP or MQTT. More importantly, you'll simulate a real-world use case from start to finish, preparing you for a larger and more advanced deployments. You should also consider adding basic error handling and basic security features. For instance, checking if the sensor is connected properly, ensuring if Wi-Fi connection is stable. So a lot of things we can do depending on your programming skills will dictate how far you go in this project. So while the Wokwi simulator provides a safe environment that we can test in, the same principles apply in the physical projects as well. So let's look briefly at storage and data logging. Okay. Now, we don't have a whole lot left in this lecture, but we still got probably 4 or 5 minutes, okay? Once your Pi is on a network, you can access it remotely using SSH or tools like VNC. This allows you to update code, reboot the device, or monitor logs without being physically near it. CEN jobs in Linux can be used to automate tasks like reading sensors every 15 minutes or sending data every hour. As you complete your project, keep these ideas in mind. Your final submission will include Python code for reading and logging sensor data, simulated hardware connections in WOKWI, and comments explaining how data flows through the system. You'll also document your design choices and reflect how they align with real-world IoT deployments. So let's wrap things up. The Raspberry Pi is flexible, it's accessible, and it's a powerful platform for building and testing IoT systems. It bridges the gap between low-level sensor control and high-level data processing and cloud integration. Whether you're monitoring soil moisture on a farm, or tracking energy usage in a building, or experimenting with smart home automation, the Raspberry Pi is an ideal entry point for prototyping and scaling up your ideas. By mastering this platform, you're gaining a practical foundation for building your own IoT solution and understanding the full pipeline, from data collection and processing to network communication and remote management. So that wraps up what I wanted to cover here in Module 5 relative to the Raspberry Pi SBC. When we move on, the next chapter, we're going to look at the IoT through Arduino in Module 6. All right, Module 6, it's not the same kind of project you'll have for Raspberry Pi. In Module 6, it'll be a paper. And we'll talk more about that in Module 6. Okay. So we'll see you over there.